In this chapter, we will zoom into the internal architecture and provide a classification of DBMSs along various dimensions. The overview of the chapter is straightforward. We start by discussing the various components that together make up a DBMS. Next, we will provide a classification of DBMSs in terms of data model, degree of simultaneous access, architecture, and usage. Here you can see an overview of the key components of a database management system. Note that the figure is by no means exhaustive. Depending upon the vendor and implementation, some components may be left out and others added. To the left, you can see various ways of interacting with the DBMS. DDL statements are meant to create data definitions, which will be stored in a catalog. Interactive queries are typically executed from a front-end tool, such as a command line interface, simple graphical user interface, or forms-based interface. Applications interact with the DBMS using embedded DML statements. Finally, the DBA or database administrator can use various database tools to maintain or fine-tune the DBMS. To facilitate all these usages, the DBMS will provide various interfaces which will invoke its components. The most important components are the connection manager, the security manager, the DML compiler, various database utilities, the query processor, and the storage manager. The query processor consists of a DML compiler, query parser, query rewriter, query optimizer, and query executor. The storage manager includes a transaction manager, buffer manager, lock manager, and log manager. All these components interact in various ways, depending upon which database task is executed. The database itself contains the raw data, or database state, the catalog with the database scheme and other metadata information, and the indices, which are part of the physical scheme, providing quick access to the data. In what follows, we will discuss each of these components more extensively. The connection manager allows to set up a database connection. It can be set up locally as well as through a network, which is more common. It will verify the logon credentials, such as username and password, and will return a connection handle. A database connection can either run as a single process or as a thread within a process. Remember, a thread represents an execution path within a process and represents the smallest unit of processor scheduling. Multiple threads can run within a process and share common resources such as memory. The security manager will verify whether the user has the right privileges to execute the database actions required. Remember, some users can have read access whilst others have write access. This can be further refined to certain parts of the data. The security manager will retrieve these privileges from the catalog. The DDL compiler compiles the data definitions specified in DDL. Ideally, the DBMS should foresee 3 DDLs, one for the physical scheme, one for the conceptual scheme, and one for the external scheme. Most implementations, however, have only one DDL with 3 different sets of instructions. This is the case for most relational databases which use SQL as their DDL. The DDL compiler will first parse the DDL definitions and check their syntactical correctness. It will then translate the data definitions to an internal format and generate errors if required. Upon successful compilation, it will register the data definitions in the catalog where they can be used by all the other components of the DBMS. The query processor is one of the most important parts of a DBMS. It will assist in the execution of database queries such as retrieval of data, insertion of data, update of data, and removal of data from the database. Although most DBMS vendors have their own proprietary query processor, it usually includes a DML compiler, query parser, query rewriter, query optimizer, and query executor. Let's provide some more detail about each of these subcomponents. Remember, DML stands for Data Manipulation Language. It provides a set of constructs to select, insert, update, and delete data. Before we provide more details about the functioning of the DML compiler, we need to elaborate a bit more on the different types of DML. The first data manipulation languages that were developed were predominantly procedural DML. These DML statements explicitly specified how to navigate in the database to locate and modify the data. They usually started by positioning on one specific record or data instance and navigate from there onwards to other records using memory pointers. This is why procedural DML is also referred to as record-at-a-time DML. DBMSs with procedural DML did not have a query processor. In other words, the application developer had to explicitly define the query optimization and execution himself. To write efficient queries, the developer had to know all the details of the DBMS. It is clear that this is not a preferred implementation, since it seriously complicates the efficiency, transparency, and maintenance of the database applications. Unfortunately, many firms are still struggling with procedural DML applications due to the legacy DBMSs which are still being used nowadays. Declarative DML is a more efficient implementation. Here, the DML statements specify what data should be retrieved or what changes should be made rather than how this should be done. The DBMS will then autonomically determine the physical execution in terms of access path and navigational strategy. In other words, the DBMS hides the implementation details from the application developer, which facilitates the development of database applications. Declarative DML is usually set-at-a-time DML, whereby sets of records or data instances can be retrieved at once and provided to the application. A popular example of declarative DML is SQL, which we will extensively discuss in a later chapter. Many applications work with data stored in a database. To access a database and work with it, DML statements will be directly embedded in the host language. Obviously, both host language and DML should be able to successfully interact and exchange data. As an example, think about a Java application with embedded SQL. Here you can see an example of this. Without going into any language or syntax specifics, this Java application initiates a database connection with a given username and password executes an SQL query which asks for the employee names together with their department names, and then iterates through the results, whereby at each step the employee name and corresponding department name is displayed to the screen. The embedded SQL DML statements are highlighted in red. Embedding DML statements into a host language is not as straightforward as it seems at first sight. More specifically, the data structures of the DBMS and the DML may be different from the data structures of the host language. In our example, we used Java, which is an object-oriented host language, and combined it with MySQL, which is a relational DBMS using SQL DML. The mapping between object-oriented and relational concepts is often referred to as the impedance mismatch problem. It can be solved in various ways. First, we can choose a host language and DBMS with comparable data structures. In other words, we combine Java with an object-oriented DBMS, which will allow transparent retrieval and storage of data. As an alternative, we could also opt to use middleware to map the data structures from the DBMS to the host language and vice versa. Both options have their pros and cons and will be discussed more extensively in later chapters. Here you can see the impedance mismatch problem illustrated once more. To the left, we have a Java class employee with characteristics such as employee ID, name, gender, and department number. It also has getter and setter methods to implement the OO principle of information hiding. To the right, we have the corresponding SQL DDL, which essentially stores information in a tabular format, as you can see illustrated. The DML compiler will start by extracting the DML statements from the host language. It will then closely collaborate with the query parser, query rewriter, query optimizer, and query executor for executing the DML statements. Errors will be generated and reported if necessary. The query parser will parse the query into an internal representation format. It will check the query for syntactical and semantical correctness. To do so, it will make extensive use of the catalog to verify if the data concepts referred to are properly defined there, and see if the integrity constraints have been respected. Again, errors will be generated and reported if necessary. The query rewriter will optimize the query independent of the current database state. It will simplify it using a set of predefined rules and heuristics which are DBMS specific. In a relational database management system, nested queries might be reformulated or flattened to join queries. We will discuss both types of queries more extensively in a later chapter. The query optimizer is a very important component of the query processor. It will optimize the query based upon the current database state. It can hereby make use of predefined indices which are part of the physical scheme and provide quick access to the data. The query optimizer will come up with various query execution plans and evaluate their cost by aggregating the estimate number of input-output operations, the plan's estimated CPU processing cost, and the plan's estimated execution time into the total estimated response time. Obviously, a good execution plan should have a low response time. It is important to note that the response time is estimated and thus not exact. The estimates are made using catalog information combined with statistical inference procedures. More specifically, empirical distributions of the data will be calculated and summarized by their means, standard deviations, etc. Coming up with accurate estimates is crucial to have a good query optimizer. Finding an optimal execution path is essentially a classical search or optimization problem, whereby techniques such as dynamic programming can be used. The result of the optimization procedure is a final execution plan, which is then handed over to the query executor. As already mentioned, the implementation of the query optimizer depends upon the type of DBMS and the vendor, and is considered to be a key competitive asset. The storage manager is another important component of the DBMS. It consists of a transaction manager, buffer manager, lock manager, and log manager. Let's zoom into some more detail. The transaction manager supervises the execution of database transactions. Remember, a database transaction is a sequence of read-write operations considered to be an atomic unit. The transaction manager will create a schedule with interleaved read-write operations to improve overall efficiency and execution performance. It also guarantees the atomicity, consistency, isolation, and durability or ACID properties in a multi-user environment. It allows to commit a transaction upon successful execution, such that the effects can be made permanent, and roll back a transaction upon unsuccessful execution, such that any inconsistent or bad data can be avoided. The buffer manager is responsible for managing the buffer or cache of the DBMS. This is part of the internal memory, which the DBMS will check first when data needs to be retrieved. Obviously, retrieving data from the buffer is significantly faster than retrieving it from external disk-based storage. The buffer manager is responsible for intelligently caching the data in the buffer for speedy access. It needs to continuously monitor the buffer and decide which content should be removed and which one added. In case data in the buffer has been updated, it must also synchronize the corresponding external memory to make sure updates are made permanent. Furthermore, it must also be able to serve multiple transactions simultaneously. Hence, it will closely interact with the lock manager to provide concurrency control support. A simple buffering strategy is based upon data locality, which states that data recently retrieved is likely to be retrieved again. Another strategy uses the 2080 law, which implies that 80% of the transactions read or write only 20% of the data. Finally, when the buffer is full, the buffer manager needs to adopt a smart replacement strategy to decide which content should be removed. The lock manager is an essential component for providing concurrency control. More specifically, before a transaction can read or write a database object, it must acquire a lock. A read lock allows a transaction to read a database object, whereas a write lock allows a transaction to update it. To enforce transaction atomicity and consistency, a locked database object may prevent other transactions from using it. The lock manager is responsible for assigning, releasing, and recording locks in the catalog. It will hereby make use of a locking protocol which describes the locking rules, and a lock table with the lock information. The lock manager keeps track of all database operations in a log file. It will be called upon to undo actions of aborted transactions or during crash recovery. Besides the components we discussed before, a DBMS also comes with various utilities. A loading utility allows to populate the database with information from a variety of different sources, such as another DBMS, text files, Excel files, etc. A reorganization utility automatically reorganizes the data for improved performance. Performance monitoring utilities report various KPIs, such as storage space consumed, query response times, and transaction throughput rates to monitor the performance of a DBMS. User management utilities allow to create user groups or accounts and assign privileges to them. Finally, also a backup and recovery utility is typically included. As we already mentioned before, a DBMS needs to interact with various parties, such as a database designer, a database administrator, an application, or even an end user. To facilitate this communication, it will provide various interfaces, such as a web-based interface, a standalone query language interface, a command line interface, a forms-based interface, a graphical user interface, a natural language interface, an admin interface, and a network interface. Here you can see an example of the MySQL Workbench interface. You can see the management window with the management, instance, performance, and schemes section. The query window provides an editor to write SQL queries. In our case, we wrote a simple SQL query to ask for all information from the supplier table. The results window displays the results of the execution of the query. The log window provides a log with actions and possible errors. We can hereby conclude the discussion of the architecture of a DBMS. In what follows, we will present a categorization of DBMSs according to various criteria. We will discuss DBMSs based upon data model, simultaneous access, architecture, and usage. Note that our categorization is not to be interpreted in an exhaustive or exclusive way. It can thus be that a DBMS falls into multiple categories simultaneously. Also, other categories might be considered. Various types of data models have been introduced for building conceptual, logical, and implementation database models. We will briefly summarize them here and provide more detail in subsequent chapters. Hierarchical DBMSs adopt a hierarchical data model. The DML is procedural and record-oriented. No query processor is included. The definitions of the conceptual and physical scheme are intertwined, which is not nice from a usability, efficiency, and maintenance perspective. Popular examples are IMS from IBM and the registry in Microsoft Windows. Network DBMSs use a network data model. One of the most popular types are codicil DBMSs, which implement the codicil data model. Also here, the DML is procedural and record-oriented, and no query processor is available. Consequently, the definitions of the conceptual and physical scheme are also intertwined. Popular examples are CA IDMS from Computer Associates, UDS from Siemens Nixdorf, DMS 1100 from Unisys, and Image from HP. both hierarchical and codicil DBMSs or legacy database software. Relational DBMSs use the relational data model and are the most popular in industry nowadays. They typically use SQL or structured query language for both DDL and DML operations. SQL is declarative and set-oriented. A query processor is provided to optimize and execute the database queries. Data independence is available thanks to a strict separation between the conceptual and physical scheme. This makes it very attractive to develop powerful database applications. Popular examples are MySQL, which is open source and maintained by Oracle, the Oracle DBMS, also provided by Oracle, DB2 from IBM, and Microsoft SQL Server from Microsoft. Object-oriented DBMSs are based upon the object-oriented data model. Remember, an object encapsulates both variables and methods. When combining an OODBMS with an OO programming language, there is no impedance mismatch, since the objects can be transparently stored and retrieved from the database. Examples of OODBMSs are DB4O, which is an open source OODBMS maintained by Versant, ObjectDB from ObjectDB software, and Gemstone from VMware. OODBMSs are not that popular in the industry due to their complexity. An object relational or extended relational DBMS uses a relational model extended with object-oriented concepts such as user-defined types, user-defined functions, collections, inheritance, and behavior. As with pure relational DBMSs, the DML is SQL, which is declarative and set-oriented. A query processor is available for query optimization. Most relational DBMSs, such as Oracle, DB2, and Microsoft SQL Server, incorporate object relational extensions. DBMSs can also be categorized based upon the degree of simultaneous access. In a single user system, only one user at a time is allowed to work with the DBMS. Obviously, this is not that desirable in a networked environment. Multi-user systems allow multiple users to simultaneously interact with the database in a distributed environment. To do so successfully, the DBMS should support multi-threading and provide facilities for concurrency control. A dispatcher component will then typically distribute the various incoming database requests among server instances or threads. The architectural development of DBMSs is quite similar to that of computer systems in general. In a centralized DBMS architecture, the data is maintained on a centralized server. All queries will then have to be processed by this single server. In a client-server DBMS architecture, active clients will request services from passive servers. A fat client variant stores more processing functionality on the client, whereas a fat server variant puts more on the server. The N-tier DBMS architecture is a straightforward extension of the client-server architecture. A popular example is a client with the GUI functionality, an application server with the various applications, a database server with the DBMS and database, and a web server for the web-based access. The communication between these various servers is then handled by middleware. In a cloud DBMS architecture, the DBMS and database will be hosted by a third-party cloud provider. The data itself can then be distributed across multiple computers in a network, such as the internet. Although this is a cheap solution, it is usually less performing in terms of processing queries or other database transactions. Popular examples are the Apache Cassandra project and Google's Big Table. A federated DBMS is a DBMS which provides a uniform interface to multiple underlying data sources, such as other DBMSs, file systems, document management systems, etc. By doing so, it aims at hiding the underlying storage details to facilitate data access. An in-memory DBMS stores all data in internal memory instead of expensive external storage, such as disk. It is often used for real-time purposes, such as in telco or defense applications. Periodic snapshots to external storage can be taken in order to support data persistence. A popular example of an in-memory DBMS is SAP's HANA product. DBMSs can also be characterized based on usage. In what follows, we will discuss operational versus tactical or strategical usage, big data and analytics, XML DBMSs, multimedia DBMSs, GIS DBMSs, sensor DBMSs, mobile DBMSs, and open source DBMSs. Online transaction processing, or OLTP DBMSs, focus on managing operational or transactional data. Think of a point of sale or POS application in a supermarket where data needs to be stored about each purchase transaction, such as the customer information, products purchased, the prices paid, the location of the purchase, and the timing of the purchase. For these applications, the database server must be able to process lots of simple transactions per unit of time. Also, the transactions are initiated in real time, simultaneously, by lots of users and applications. Hence, the DBMS must have good support for processing a high volume of short, simple queries. Online analytical processing, or OLAP DBMSs, focus on using operational data for tactical or strategical decision making. Here, a limited number of users will formulate complex queries to analyze huge amounts of data. The DBMS should allow to efficiently process these complex queries, which often come in smaller volumes. Big data and analytics are all around these days. IBM projects that every day we generate 2.5 quintillion bytes of data. This is a lot compared to traditional database applications. Hence, new database technologies have been introduced to efficiently cope with big data. NoSQL, which stands for Not Only SQL, is one of these newer technologies. NoSQL databases abandon the well-known and popular relational database scheme in favor of a more flexible, schemaless database structure. This is especially handy to store unstructured information, such as emails, text documents, Twitter tweets, Facebook posts, etc. One of their key advantages is that they also more easily horizontally scale in terms of storage. Four popular types of NoSQL database technologies are key value-based databases such as CouchDB, document-based databases such as MongoDB, column-based databases such as Cassandra, and graph-based databases such as Neo4j. We will discuss these into more detail in later chapters. XML is a data representation standard which is used to represent the content of data. Here, you can see an example of an XML specification of my personal details. You can see that we have various tags such as employee, first name, last name, etc. The address tag is further subdivided in street, number, zip code, city, and country tags. Obviously, it is important that every tag is properly closed. An XML specification essentially represents data in a hierarchical way. To the right, you can see the tree corresponding to our XML specification. XML is a very popular standard to exchange data between various applications. Native XML DBMSs store XML data by using the logical, intrinsic structure of the XML document. More specifically, they map the hierarchical or tree structure of an XML document to a physical storage structure. Enabled XML DBMSs are existing DBMSs which are extended with facilities to store XML data and structured data in an integrated and transparent way. Both types of DBMSs also provide facilities to query XML data. Multimedia DBMSs allow the storage of multimedia data such as text, images, audio, video, 3D games, CAD designs, etc. They should also provide content-based query facilities such as find images of Bart or find images of people who look like Bart. Streaming facilities should also be included to stream multimedia output. Clearly, these are very resource-intensive transactions, which may require specific hardware support. Note that multimedia data is usually stored as a binary large object or blob. A GIS DBMS allows to store and query spatial data. An example query could be: determine the geological decomposition of a specific region. A sensor DBMS allows to manage sensor data such as biometric data obtained from wearables or telematics data which continuously records driving behavior. Ideally, it should allow to formulate application-specific queries such as spatial temporal queries which ask for the shortest path between two locations given the current state of the traffic. Mobile DBMSs are the type of DBMSs running on smartphones, tablets, and other mobile devices. They should obviously have special properties. They should always be online, have a small footprint, and be able to cope with limited processing power, storage, and battery life. Depending upon the application, they could connect and synchronize to a central DBMS. Ideally, they should be capable to handle queries and also support self-management without the intervention of a DBA. Some popular examples are Oracle Lite, Sybase SQL Anywhere, Microsoft SQL Server Compact, SQLite, and IBM DB2 Every Place. Finally, open source DBMSs are DBMSs of which the code is publicly available and can be extended by anyone. Hence, this has the advantage of having a large development community working on the product. They are very popular for small business applications and in developing countries where budgets are limited. Most of the open source DBMSs can be obtained from sourceforge.net, which is a well-known website for open source software. Some examples are MySQL, which is a relational DBMS maintained by Oracle, PostgreSQL, which is also relational and maintained by the PostgreSQL Global Development Group, Twig, which is an object-oriented DBMS maintained by Google, and Purst, which is also an OODBMS maintained by MacObject. To conclude, in this chapter, we first zoomed into the architecture of a DBMS. We extensively discussed the various components that together make up a DBMS. Next, we provided a classification of DBMSs in terms of data model, degree of simultaneous access, architecture, and usage. Many of the concepts discussed in this chapter will be elaborated further in subsequent chapters.